K square by r square equal to 2 by 5. M cancel. From that we get here K square by r square is equal to 2 by 5. What here? R square by K square. That means 5 by 2. Substitute here 5 by 2. That means 2 plus 5, 7. Tan 45, 1. 2 by 7. Nearly that equal to get here 0.3. Nearly, no problem. But the minimum coefficient of friction required to roll the sphere from this surface is 0.3. For example, say the coefficient of friction of this surface and saying 0.25. A sphere is placed on this surface. Is it possible to roll? No, because with this friction not possible. Minimum friction coefficient of friction required is 0.3. So from that we can calculate what is the value. For example, they given like that. The coefficient of friction of this surface is 0.7. The inclined angle 45. Which body is capable to roll on the inclined surface? Once again repeating the coefficient of friction of this surface I am saying 0.7 and the inclined angle is 45 degrees. Same mass of the bodies are placed on the ring, on the inclined surface, ring, solid sphere, cylinder, other bodies. Which body is capable to roll on this inclined? First you are going to calculate what is the minimum coefficient of friction in case of ring. What is the minimum coefficient of friction required in case of solid sphere? What is the minimum coefficient of friction required in case of cylinder? So that when you calculate by using the tan theta by 1 plus k square, r square by k square. Here tan theta 45. So you get here 1 by 2, that equals 0.5. So for the in case of ring, the minimum coefficient of friction is 0.5. No problem. Here the given surface has a coefficient of friction 0.7. That means this value is more than this one. So in that way, the coefficient of friction is more than this value. No problem. Otherwise, body can't run. Here, in case of solid sphere, just now we calculate, we get here 0.3. So it is not possible because the 0.3 is less than. Sorry, no problem. It is also possible. Minimum 0.3. Given 0.7. Yes, it is possible. For example, it is given 0.2. In that case, there is no chance to roll the body on the inclined surface. Ring is not possible to roll. Solid sphere also not possible to roll on the inclined surface because the minimum coefficient of friction is less than the given surface. So that is the conditions. What is the torque acting on this? Get tau equal to I alpha. So from that also we get another concept. Torque tau equal to I alpha. Torque means R into force F, that equal to I into alpha means you can write as A equal to R alpha. From that by get A by R. So the linear acceleration in terms of frictions we get here A equal to R square F by I. So that is the linear acceleration in terms of friction force and in terms of moment of inertia. I plus we can write as here mk square. So that equal to F by m into R square by k square. So that is the linear acceleration in terms of friction force F by m R square by k square. So that is about the inclined plane, rolling motion on inclined plane. See one more example I will explain. Just I am going to give one concept on a rod, not related to rolling motion. Just I am going to the one concept of length m, mass m is placed on the ground like that. When it released, what happens? It falls down like that. So it is not rolling, it is rotatory motion. With respect to this axis, the rod, when it's released, it falls like that. What is the velocity of this rod? What is the velocity of this end before it's the ground? ఇక్కడ హిట్ అయినప్పుడు what is the velocity of this rod? The rod is falls like that. Now the rod is at this position. What is the velocity of this free end of the rod when it is at an angle theta? So different cases is there. So I am explaining here. Just rod, mass m, length l, mass m, center of mass of the rod. When it is like this, the energy nothing but potential energy. Here the height of the body from the ground nothing but center of mass from the ground at a height here L by 2. Total length is L. That's why this becomes L by 2. So the potential energy of this rod we get here mg into L by 2. When it falls like this, it gains some kinetic energy. Here rotatory motion, not rolling motion. So the kinetic energy is equal to, can write as here half m. Kinetic energy in case of rotatory motion. So you can write as here half I omega square. Half I omega square. So now what is the velocity of this free end of the rod when it touches the ground? So fall like that. This end touches the ground with certain velocity. What is that velocity? Just myself, I am assuming that velocity is v. Or angular velocity, no problem, just assume omega. From that initially it is at rest, that's why that has the only potential energy mg L by 2. When fall like this, now it is on the ground. In this situation, initial potential energy mg L by 2. When it is fall on the ground at this position, potential energy is equal to 0. The change in potential energy nothing but gain in kinetic energy. The loss of potential energy is equal to the gain in kinetic energy from law of conservation of energy. So we can write as here delta PE, loss of potential energy. This one minus this one, this one minus this one, no problem. Mg into L by 2. This is equal to the gain in kinetic energy. So what is the kinetic energy of the rotating body of I omega square? So I am taking this here half I omega square is equal to mg into L by 2. Here I is moment of inertia of this rod with respect to this axis, because the body is rotated like this with respect to, with support of this point it can rotate. That's why axis, rotating axis to this body in this situation. So the moment of inertia of this rod with respect to this axis, the axis passing through one angle perpendicular to the plane. That's why moment of inertia of the rod with respect to this axis I equal to the formula ml square by 3. Substitute here 1 by 2 m L square by 3 omega square, that equal to mg L by 2. Both sides mm get cancelled. Here 2 also cancelled. Here one L is cancelled. Omega square is equal to 3g by L. Omega equal to under root 3g by L. When the rod is touches the ground with angular velocity is given by omega is equal to under root 3g by L. I am asking what is the linear velocity? From this fixed point, this free end is at a distance L. Angular velocity of the particle, this particle is remains same. In rotatory motion, angular velocity of the particles of the system remains same, but linear velocity is not same. Here the free end from the fixed point is at a distance L. That's why before hits the ground, the linear velocity, this is the angular velocity, but I am asking now what is the linear velocity of this free end before hits the ground. So V equal to, the formula R omega means perpendicular distance. R is here perpendicular distance from the axis of rotation. That means here the free end from this at a distance L. We get here V equal to L omega. That equal to L into omega means under root 3g by L. So L send inside under root 3g L square by L. So you get here V equal to root 3g L. So this is the angular velocity before it's the ground. This is the linear velocity before it's the ground. For example, okay, when body falls like this, it reaches the ground. At the ground, the linear velocity and angular velocity. I am asking, not here at midpoint at this position, so like this. What is the velocity of the rod when falls vertical direction to certain angle like this? At this position, what is the velocity? What is the angular velocity? What is the linear velocity of this free end of the rod when reaches to this point from here to here? Here velocity is 0. At this position velocity you know from these values. What is the velocity? From that to get here first. It is an angle theta. Rod initially like this. Length here, length L, mass M. Now it is at certain position, makes an angle theta. What is the velocity of this free end of the rod when it reaches, it falls back? At this position, what is the omega and what is the V value? Once you know the omega value, you can easily calculate the V value because V equal to the formula. From axis of rotation, this particle is at a distance, perpendicular distance, nothing but length. We can write as V equal to L omega. But what is the value of omega? Going to calculate. Theta. Initially, it is like this. The center of mass of this system at a height L by 2. So the initial potential energy of the rod we can write as mgl by 2. Now the rod displaced from this position to like this. The center of mass also shifted to certain position. So what is this height? Just assume yourself. From here to here center of mass, exactly center. This is theta. From here to here we know the value L by 2. So this is theta. This is also becomes theta. Sin theta equal to cos theta equal to as you wish. So sin theta equal to you can write as here opposite by hypotenuse. Cos theta equal to adjacent by hypotenuse. Now I am going to calculate the potential energy in this situation. So when rod is displaced from this position to this position, the center of mass is at this height. So from this triangle, just assume cos theta equal to adjacent by hypotenuse. That's why you get here cos theta is equal to adjacent means height of this body. We don't know some x by hypotenuse L by 2. So from that x equal to L by 2 cos theta. So the height of this part L by 2 cos theta. So now the potential energy of this rod in this situation PE2. I am taking as here mg. H means L by 2 cos theta. When the rod displaced from here to here, initially potential energy is mg of L by 2. And finally at this position the potential energy of the rod mg of L by 2 cos theta. The change in potential energy we can write as here delta PE, loss of potential energy, mg L by 2 minus mg L by 2 cos theta. So from that we can write as here mg of L by 2 of 1 minus cos theta. Loss in potential energy. That is nothing but gain in kinetic energy. So we can write as here simply half I omega square. Close. So from that I means moment of inertia of this rod with respect to this axis, that is we know the value mn square by 3 into omega square, that equal to mg L by 2 of 1 minus cos theta. So from that get cancelled. Here L also cancel. Omega square 2 also cancel. Omega square equal to 3g of 1 minus cos theta by L is there. Omega equal to under root of. So that is the angular velocity of the free end of the rod or end of the rod, no problem, because angular velocity remains constant. So end of the rod or rod, the angular velocity of the rod when it displaced from this vertical position to an angle theta is given by. Before I solve this case, when it falls on the ground, when it falls on the ground means from this position, it falls on the ground means the angle theta is nothing but 90. So in that case we can write as a under root 3g by L 1 minus cos 90 0. That is also we get here root 3g by L. Before also we get the same value, but basic formula is this one. From that they are asking what is the velocity, angular velocity of the rod when it displaced from vertical position to 60 degrees. Theta equals substitute here. In some situations, reverse asking, the rod is fall from vertical position to onto the ground. What is the angular velocity of this rod when it makes angle of 30 degrees with horizontal? When it makes an angle of 30 degrees with horizontal, then we are required to this value because in the formula theta is nothing but with the vertical position. So in some cases, if they given this value, then we are going to calculate theta first. After that, substitute the value. Same again. What is the linear velocity? Here also v equal to L omega. L into omega means under root 3g of L, 3g of 1 minus cos theta by L. L side inside L square. You get here 3Lg of 1 minus cos theta. For example, what is the linear velocity at this point? From the fixed point, this is at a distance L by 2. So in this case, the linear velocity can write as v equal to L by 2 into omega. So omega is the value under root of 3g of 1 minus cos theta by L. L by 2 nothing but this one. Linear velocity of this point. Angular velocity of this point is nothing but same because angular velocity of the body in rotatory motion, each particle having the same velocity. So that is